Thank you very much, Henry. Thank you for the kind introduction. Thanks again for inviting me and giving me the opportunity to talk about the research we have been doing here in Southeast Michigan related to vehicle to everything connectivity, and in particular building such an infrastructure on Highway I-275. So let me start with introducing the team of people who are working on this project. So as you can see, this is a CCAT project, and so we are part of this set of projects CCAT is running, and they are really exciting. And in this particular one, we are working together with Professor Harvey Bell. So Harvey used to work at General Motors for about 39 years before he joined the University of Michigan. So he certainly has the perspective of the industry when we are doing academic research, and he's keeping us streamlined when to make sure that whatever we do is applicable. Professor Jerry Lynch is the head of the Civil and Environmental Engineering Department, and Jerry has an extensive experience on infrastructure monitoring, and as a matter of fact, he already has a working infrastructure at some of the bridges at I-275, and we can actually leverage some of those things in this project. And Professor Yafeng Yin is also a professor in Civil and Environmental Engineering, and he's an expert on optimization and game theory of large-scale systems. And when we look, and in particular, applications to transportation systems. So his expertise are very much needed in order to succeed in this project. On the right side, you can see a couple of names. So those are the undergrads, grad students, and postdocs who are really doing the heavy lifting regarding this project, and they are pushing forward. And on the bottom, you can see 4 collaborators, 3 companies, and also government. So today we're going to talk about trucks. So Navistar is actually our collaborator on this project, and they are the ones who are allowing us to basically run real trucks on real roads. And as I will show you in the presentation, this is very important in this project. And Ford Motor Company is very much interested in helping us in traffic predictions. That's one of their big interests now, and people listed here are helping us a lot on that. We are going to talk about CV2X today. So we need CV2X devices, and Comsignia is the company who is providing us with both the devices as well as with the technical support to be able to operate these devices. And finally, we very much thank MDOT because indeed, they are the ones who enable us to deploy the technology on real Michigan roads and try to prove some benefits and day one benefits which can come up from this technology. So let me start with some high-level picture in what we try to achieve here. And maybe some of these things will be not completely clear at this slide, but as I go further in the presentation, I can try to give more details. So first of all, we start with the high-level societal benefits. Our main focus today is going to be reducing energy consumption of vehicles. But of course, if we are able to do that by not burning so much fuel or not consuming so much electric energy, that also going to have a big impact on greenhouse gas emissions and also other pollutants. So those we are expecting to be reduced. And finally, if we are able to improve the transportation system, then we expect an increase of productivity of the economy, which we also think is going to be one of the big impacts of this project. And the way we are trying to achieve here, there are 2 key parts in this lower box. So first of all, we are building the infrastructure, okay, along the highway. And the goal of this infrastructure is typically very high level. We try to maximize the throughput We want to make sure that we have a business model here, so we can sustain the installation cost and the operation cost. And of course, maybe as any infrastructure, it has a finite lifetime. We want to make sure that we can maximize that lifetime. And then on the right, you can see what I'm going to go more details is what we call connected and automated trucks. So trucks' job is to deliver goods in time. And of course, they try to do it with as little fuel consumed as possible. Fuel doesn't necessarily mean fossil fuels. It could be an electric vehicle or hybrid electric vehicles. The ideas which I'm going to present today actually apply to any type of trucks, not just internal combustion engine ones. And of course, safety is crucial to maintain, both in terms of making sure that human life is not in danger, but also in terms of that if any safety compromise happens, a little accident occurs, that can actually compromise the first objective, which is delivering things in time. And the whole thing in the middle, which is going to bound these players together, is going to be CV2X communication. So it's basically cellular vehicle to everything communication. It's a wireless technology. And I will talk a little bit more about it. What does this mean? And you can see there is an important class of participants, which are still listed here at the bottom, which we call them connected human-driven vehicles. So these will be vehicles, we are not necessarily automated, but they possess this connected technology. And I will demonstrate that it's actually important to have these in order to achieve the goals which we are trying to do in this research. So let me show you a picture of the type of vehicles we are looking at. So this is what we call a Class A truck. Okay, so when it's fully loaded, it's about 30 tons. So it's a really large animal of our roadways. And let's take a look at a little bit how important these vehicles are for our economy. So once we're looking at the goods transported in the United States, in terms of value, in terms of weight, or in terms of ton miles, then it turns out that heavy-duty vehicles are a key player in this field. We can say that in terms of value and tons, the majority of our goods, those things which these days we are mainly ordering online, are actually delivered by these road giants. So it's it shows that it has an utmost importance to actually keep this running. On the other hand, once you look at the fuel consumption of these vehicles, and if you compare it with the different classes of trucks, of course, as the number increases, the heavier, the larger the trucks are, then you can see that more than 60% of the fuel consumed by trucks on US roads are actually consumed by Class A trucks. That means that if we are able to target this population of vehicles, then we should be able to make a big impact in terms of the energy economy of the country. So once we started to work with vehicles, we didn't start it with these large ones. Obviously, as I will show later, there are many complications coming from the size. So we actually started with something like this little, okay? So this was actually the first vehicle we built. This was through M-City, which is a test track at the University of Michigan. And it was a fantastic opportunity that we could actually build a vehicle, test it there, and it's a safe environment. So we are very glad that we could use those facilities. So what we did first, we actually started to run some initial experiments with the vehicle. And this is one of them, what I'm showing here. As a matter of fact, what happens here, there are 3 vehicles in front of our automated vehicle. They are all human driven. And as a matter of fact, the vehicle we built is only sensing the one right in front of it. And you can see a sequence of braking happening here. These vehicles are braking harder and harder. And what happened with the little Kia Soul in the end, it was really harsh braking. As a matter of fact, after a day of testing, all the students were complaining because the safety belts were hurting their shoulder because sometimes 60 or 80% of their weight was on the safety belt. The accelerations were so high. So it turns out that once you add connectivity to the system, you can make huge improvements in it. So I'm showing here another experiment. And in this case, the vehicle was a connected automated vehicle, which means it didn't just sense the vehicle right in front of it, but it was actually getting information from those distant vehicles. And what it meant is that it basically started to brake much earlier than in the previous case, and also resulted that braking was actually much more mild. So as a matter of fact, if you rode this vehicle through these experiments, you could drink your cup of coffee and not a droplet would be spilled out because the accelerations were so little, decelerations were so little, and it was a very, very smooth ride, okay? So we could see these large benefits on a test track. We wanted to see, can we maintain these benefits once we start to run vehicles on railroad, okay? So then we went to rural Michigan and we found this beautiful piece of road. It's 8 miles long and there's no interruption of driving. Okay, so it's the American dream. Basically, you can just drive. There are roads which are crossing you, but you always have the advantage. Okay, and you can see some of the vehicles. We were running this experiment. Of course, the big fight was always that who's going to drive the Dodge Challenger. And I think in this day, this guy was the lucky one, and he drove that in the whole day. And what we really did was basically we tested these systems, these connected and automated vehicle, and tried to understand, how does it behave once it inserted into a flow of vehicles. So once we again run it in the AV mode, so basically it was just an automated vehicle, then this is what we see in these experiments. So this is one particular braking event where the front vehicle, this brown vehicle, was stepping on the brake and accelerating back. And as you can see, all the other vehicles were actually following it. And you could see that the braking is getting harsher and harsher and harsher. Actually, the AV was doing better. It was cutting back a little bit on the braking. You can see it didn't increase the braking. It actually maintained a little bit higher speed. So we could see that indeed automation is beneficial. And any of you are driving vehicles with ACC, which is essentially this automation, that'll you will probably experience something similar, that the machine is typically doing better than most of the human drivers. However, what we also added is was the connectivity, and we've seen something which was very interesting. As a matter of fact, in this case, again, the braking became much less harsher. Okay, the vehicle started to step on the brake much earlier. It was able to foresee what is happening, and the speed reduction was much less. And we were very happy with these results, and this is what we really wanted to see. We wanted to see these effect of this vehicle on the traffic flow as a matter of fact. But once we started to crack the data and analyze it, we found something very interesting, which was kind of a hidden jewel we didn't really think about. It was really related to energy. So through these experiments, which of course was a very limited set of experiments, only a couple of 100 miles of driving, and it was on a flat road, and it was on these ideal conditions. But what we have seen that just because of the connectivity, you could save 19% of energy, and that's a huge number. So we were really excited about it, and we said, well, this should apply not just to our little vehicle, but any vehicles of any type of powertrain and any weight and so on. So then we talked to Navistar and showed some of these results to them. They also get excited but said, well, wait a minute, these vehicles are way much bigger. Let's take a look at whether the potential you're saying here is really there. So well, rather than going back to the road and keep running the experiments again, we actually took the data, because we already had the data collected from those vehicles, and we built a high fidelity simulation platform where essentially we put the truck behind them. And once we started to run it, we were able to produce, what the truck would have done if it was there. Okay, so we have seen something like this. In this case, rather than just showing you one braking event, I actually showing you a set of them. And you can see that the vehicle is trying to always follow the one ahead by stepping on the brake and accelerating back. Again, by adding connectivity, we expected that, again, if we optimize this system and we use the connectivity in an optimal way, then we can actually see some energy benefits. And once I show you the speed fluctuations, you can see that, well, you would expect something like that, because indeed this vehicle was braking much less and accelerating much less, i.e. burning much less fuel in these simulations. It was not as good as the experimental result with those personal vehicle, but we have seen 6 to 12% energy savings in the system. So that's still very, very substantial. And in this case, we ran a large set of simulations using a large set of data. So we are quite confident, at least that in these high fidelity simulations, we are able to achieve these benefits. However, we met a quite large problem. If you look at real systems these days, it's very unlikely that you will have a set of connected vehicles which are just in front of you sharing this information, and you can run this optimization and gain these benefits, okay? As a matter of fact, in today's or in the next few years, we will experience something what we call a connectivity graph, okay? So if you look at how a realistic system may look like, you can imagine somewhere in the traffic flow there is this connected automated truck, but the connected vehicles may be so far from it that it's not able to communicate with them. The range could be a few kilometers, and as I will talk to you later and show some results, the actual range of these equipments is maybe a few hundred meters, okay? So that means that even though we have these connected vehicles in the flow, we will not be able to utilize them to saving energy. So here comes the idea that we can bridge this gap by adding infrastructure support to the system. So essentially what we're proposing is putting a set of radios on the roadside, which allow the vehicles, the connected vehicles, to communicate. And as a matter of fact, this allows the connected automated truck to communicate with the infrastructure, but also other connected vehicles in the flow, which may be a few kilometers ahead or behind. And what I would like to demonstrate today, that indeed such a concept is feasible, both in terms of getting us the benefits which we are looking for, as well as this is something which we can potentially build. And this is exactly what the project is about. We are trying to, as a matter of fact, deploy these devices and demonstrate experimentally that indeed this is a useful concept. So there will be two kind of concepts which I'm going to talk about today, which the system can be used for. So one of them is that indeed the truck would benefit from if it knows what happens ahead. I mean, we already indicated that. So as a matter of fact, if we can make some traffic predictions with the smart infrastructure, then we can communicate those predictions to the truck, and it can use these predictions to optimize its fuel economy. On the other hand, the truck is driving in the flow, and whatever it does, it's also going to influence the vehicles behind. So as a matter of fact, by monitoring what happens upstream, we can actually provide the truck with information about, you know, how its motion is influencing the flow around. So let's take a deeper look how we can do this. Okay. So this is the section of the highway we have chosen for the deployment. So this blue section is the section of I-275. It's about 32 miles long, and what you can see is our plan where we would put these roadside units. Indeed, we have to run this plan with the FCC because this CV2X technology is relatively new. So we needed an experimental license, and recently we obtained that license. So we are ready to deploy. And you can see this section of the highway, in particular the northern section, as I will show you, is typically very heavy in terms of traffic. Indeed, these locations were determined by a lot of practical reasoning, but also many experiments and simulations, which actually helped us to determine where is the optimal location of the devices we would like to put on. Okay, so let me show some of those data and try to explain to you what we want to do. So this is an experiment we were actually running on the northern part of the I-275. What you can see in the top, in this case, we were using only vehicle-to-vehicle communication. So we had a leading vehicle, which was a few vehicles ahead of the follower vehicle. Both of these had connectivity. I will talk a little bit more about the technology in a few slides. And so that means that the vehicles were able to talk to each other, okay? So let me show you what happened in one of the experiments. So this was around this section of the highway. And you can see the leader is going to talk soon. That there is a traffic jam which is hitting. And very soon after that, the follower is also slowing down. As a matter of fact, in this particular case, had to stop. As you can see, the driver is reporting something very crazy happened here. Actually, some of the vehicles had to go to the shoulder. So indeed, this was an interesting event. As a matter of fact, there was no accident. There was no particular reason. It's simply how people drive. In this case, the effect of the leader, which he was reporting, is actually got amplified, and that's what the follower has seen. Okay. So this shows that indeed, understanding what the vehicle ahead is doing is going to help the follower to understand what is up to happen to him or her. So let me try to explain to you how does this work, okay, and why is it useful. So on the right side, you can see two trajectories of two vehicles driving in the traffic flow. They are not following directly each other. They are somewhere in the flow, okay? This is real data taken on I-275. And as you can see, I'm showing you the leaders as well as the followers trajectory, okay? And if you kind of keep staring at this picture, you can realize that, well, the leader and the follower is not doing something that different. Actually, you can see these wiggles somewhere here and there. It looks like they somehow repeated by the follower. And as a matter of fact, this is exactly what happens. So if I consider the current time, as a matter of fact, I can take some section of the leader's profile and then propagate in this prediction zone, okay, which comes out of the equations where exactly is the zone is at. And based on that, I can provide a prediction of what the follower is going to do. Okay, so again, if this is now, then nothing happened, which is dashed here, okay? So because we collected the data, we know what is up to happen. And I'm demonstrating here is actually not really a bad prediction. You can also see it pretty well when you are showing the speed prediction. It's capturing reasonably well what is the follower up to do, okay? The trick here is you don't just have to shift things in time, you have to shift things in space and time. So what I'm trying to say is that essentially the follower is going to do something very similar to the leader, sometimes later and somewhere else on the highway, okay? And on the left-hand side, actually, you can see an animation which is done by the BBC a few years ago, where as a matter of fact, you can see how this jam is propagating back along the highway. And typically the speed of the jam is going backward is about 15 miles per hour. As a matter of fact, that is nothing else but the gradient of this prediction zone, okay? So, excuse me, as the vehicles go further ahead, indeed, the prediction zone changes. So as I go further, you can see now this is the present time, you can see the prediction zone, and you can also see how well, in case of the velocity, we are actually capturing with a very, very simple model, qualitatively capturing what is going to happen with the follower vehicle. Okay, so as a matter of fact, this is a nice moment because the follower vehicle at this point is traveling with a relatively high speed, but what is up to happen that this speed is going to break down to almost zero, and after that the vehicle is going to accelerate back. Okay, and as we go further ahead, we can keep doing these predictions, and actually some of these are summarized in the paper which you can see on the left. Okay, so this shows us that there is a particular zone where we can provide predictions, and as a matter of fact, how wide this zone is also changing, and the width is of course matters because the wider the zone is, the longer the predictions we can provide. If I go back between the last two cases, you can see the width of the zone changes quite significantly. This depends on two things. It depends on the speed of the vehicles, but it also depends on how far they are from each other. The further they are, the more predictions I can have. The challenge is, of course, at some point, I'm going to hit the range of this communication, and then I won't be able to say anything, okay? So in order to make sure that we understand what is this range, we actually went and did many testing on I-275 already with this configuration. I think we have about 20 hours of data already. And based on that, we have found some interesting things, which I would like to show to you. So first of all, let me talk a little bit about the devices we are using, okay? So we get this from Consignia, and let me start with the onboard unit. So this goes on the vehicle, okay? And at the bottom, this black box, that's where the brain is at. Essentially, that's a computer that handles all the information coming in and out. You can see a bunch of wires coming out of it, ending up in this antenna, which goes on the roof of the vehicle. And that's basically where all the communication happens. Okay, so this will allow the vehicle to communicate with other vehicles. It also where the GPS antenna is hosted, so you can actually know where you are, what speed you are going at. Okay, the way you actually connect it to the vehicle is very simple. You just plug this cigarette lighter into your cigarette lighter holder, and then actually you can connect this to a laptop, so you can always monitor what's going on the device. Okay, and then you can see a tablet here. That's a very cute thing. What it can do is actually it's wirelessly connects this device, and actually there's a map in it, and on the map you can see all the other vehicles who have connectivity around you. So you can see them on the map, you can see their distance, you can see their velocity. This is a tremendous help for us during the experiments, because we always know where our other participants are, at least those we are doing the experiments with. So this is what's going on the vehicle. Now, what's supposed to go on the roadside is what we call the roadside unit. Essentially, inside this white box, there's a very similar black box, which is also a computer. You can see antennas again. There is GPS here. It also have LTE antenna, so that means that you can actually do a 5G and 4G communication. So you can actually access this device on the internet. This is very important because once it's on the roadside, often there is no opportunity to go and touch it for many weeks or months. So we should have the opportunity to remotely go in, write codes in it, send messages, or whatever we want to do, basically. And the power is very similar. In this case, of course, it's going to come from the infrastructure. It's a 12-volt power. And again, I would like to mention that, you know, even though it's called cellular vehicle to everything communication, cellular here refers to the LTE technology they are using. It does not refer to the fact that these guys should call to any cell tower or something. So it's different from your cell phone. If I call you on my cell phone, I actually call a cell tower, and a cell tower calls you. But this is peer-to-peer communication. This means that these vehicles are talking to each other directly or talking to the infrastructure directly. It doesn't require additional infrastructure for that. The carrying frequency is about 5.9 gigahertz. And again, it can share the status. So it can share GPS, speed, heading angle in every 100 milliseconds. There is a message set called basic safety message, or people call it BSM. We used to start to call it basic status message because it's not necessarily just safety. You can use it and it's still BSM. And actually, again, as I mentioned, it's peer-to-peer communication, and the protocols are broadcast and catch. So it means that vehicles are just telling, hey, this is what I'm doing, and whoever can listen with the same technology are able to receive those messages, okay? And one critical part here is the range. So we really wanted to understand experimentally what is the range of CV2X on I-275, not on a test track, not in the forest, on this piece of highway. So I'm showing you 3 different experiments. This happened on 3 different days when we basically drove these vehicles in traffic on I-275. And what I'm plotting here is the packet delivery ratio. Okay, so it's basically telling us how many packets are delivered, what is the ratio of packets delivered, depending on the distance. Okay, you can see in any of these days, we started to go down to close to 0, around 500 meters. Okay, so that would be like, I would say, the absolute range. But there are some cases we can potentially maybe have information from maybe 700 meters, or in this particular case, we got a few packets from more than a kilometer. However, if you want to have reliable communication where you have most of the packets, based on this data, we would say that the range is about 250 meters. Again, it depends on elevation, it depends a little bit on weather, it depends on the traffic around you. But we did these experiments in many, many different days, and I'm showing you some of the average scenarios. Okay, there were some better days and maybe some which were not so good as these. But we can say something that this range is about 250 meters on this section of the I-275. Okay, so let's start to understand, so why is this useful for us, and how are we going to really use this infrastructure? Okay, so imagine that we have a roadside unit. Okay, so this is on the roadside, again in about 500-meter range. It is able to see what's happening. Okay, and then you can see some of the vehicles driving by. We said they are connected vehicles, so they are carrying this CV2X technology. So once these vehicles enter the range of the roadside unit, then communication is established and messages are sent by CV2X, and you can actually have the information about those vehicles, their position, their speed, heading angle, and so on. Okay. As a matter of fact, you can pretty much send any information you want from that vehicle, and so if you want to have lane information because the vehicle is happen to detect it, then that's something we to the roadside units if you think it's useful. Okay, so on the right, I'm trying to show the concept what happens here. Again, I'm showing the position of these vehicles as a function of time as they are driving through the range of the roadside unit. Okay, and whenever they are in the range, those sections we get data, and when we got data, we can make predictions. Okay, so in this particular case, I'm showing you two vehicles. They are not consecutive vehicles. And this is just a sketch in this case, but we did it with real data and real experiments as well. And you can see that as they are going through the range, they basically emanate these prediction zones. And in particularly in this case, the two prediction zones are actually even overlapping. So there is a zone where we can probably even have better predictions because both of them are giving us data. And of course, you can also see that if they were very far from each other, then these two regions would be probably disjoint. Okay, so we are asking the question, okay, how many of these vehicles we need to have some meaningful predictions, which is, typically on most of the time. So we randomly distributed these connected vehicles in the flow and did a little math, and this is what we found. So on the horizontal axis, you can see the penetration rate of connected vehicles. Okay, so those are in percentages. So it's basically saying out of 100 vehicles, how many of having this technology. And on the vertical axis, you can see the coverage rate. And this coverage is again in terms of capability of predicting, okay? It's not in terms of physical coverage. And what we found is that if you have only 2% of these vehicles, you already have 63% coverage. If you have 5% of these vehicles, you have 92. And as a matter of fact, when you have 10% of connected vehicles, you can basically cover the entire highway in terms of predictions. Okay, so that's a very important result because we don't have to wait until we have 100% of this penetration. And of course, the trick is, if you're looking at this figure, is coming from the fact that we are monitoring these vehicles for a certain section of the road rather than just a single point, which is the traditional traffic monitoring where people use loop detectors or cameras. Okay, so this is a great opportunity because with a very small population of vehicles, we can very quickly have really, really meaningful data. So let's say we are able to do this and we are able to do these predictions. The question still remains, what should the truck do with that? Okay, so let me show you our path. Okay, there are different naming conventions my students started to give to the truck. I think the latest was Purple Haze, but I vetoed that. So we don't really have a good name yet. But what I can tell you is that it's actually good that we have another vehicle parked next to it, because this tractor itself on its own is already 9 tons. Okay, and when it's pulling something, then the fully loaded truck, again, it can be 30 tons. Okay, so it's not a real little toy. And of course, safety is our utmost importance when we are running experiments with this. So before we take them on real road, we typically run hundreds of miles experiments on closed tracks like this one, which actually happened in the Navista Proving Ground in New Carolina, Indiana. So let me show you one of the experiments which we were recently running, and I kind of try to explain to you what we found. As a matter of fact, this particular experiment, we almost found it accidentally, but something very interesting happened to us. Okay, so here is a section of the road. Okay, so you can see it from the perspective of the truck. The vehicle in front of it is what I'm going to refer the car ahead. Okay, but there is another vehicle which you don't see on this picture. That's many hundreds of meters ahead, maybe a kilometer ahead. And that's what currently is our lead vehicle. Okay, so we are wirelessly connected to these vehicles. As a matter of fact, we can respond to this vehicle also using sensors, but we can also see potentially the other vehicle if it's in the range. Okay, so let's see what's going to happen here. So when we start, first the truck driver says, I think I'm going to hit some traffic jams. As a matter of fact, these guys have tremendous experience, so we always listen to them when we are driving on the road. If you look at it as a normal driver, you wouldn't necessarily see this jam. But as you see, as most of the time, Robbie was right. And indeed, there is copy on the radio. This is going to happen soon. And there is this second question. This is also very important. The question is, do you guys see Johan? Okay, so what does that mean? So Johan was the gentleman who drove that vehicle, which was far away. Okay, and when you said see, we didn't mean actually see in naked eye or with sensors. We simply meant that in the communication devices on those little tablets, can we see, you know, the other vehicle? And the answer to this is no, too far ahead. Johan is too far. So what it meant is that in this case, the other vehicle was outside of the range, and we were not able to see it. Okay, but it would have been very useful, as I will show you, if we actually have connection with Johan. Okay, so let me show you what's happening here. So again, because safety is important, they start to instruct me. Okay, I was actually driving the vehicle ahead and telling me, okay, you know, we're gonna hit this jam, be careful. I was not seeing that. I was driving behind the truck. Okay, I had no idea what's gonna happen. And so you can see that the reason this jam was formed is a law enforcement officer parked his vehicle on the right of the road. Okay, and people were kind of afraid and they probably started to slow. So they actually created a traffic jam. You can see we are going very slow in this case of this section of the road. Okay, so and then after everything is returned, we keep running. So now it says now ACC. That means actually we are running and following the other vehicle using the sensors and the connectivity. Okay, so let me show you what this little incident means in terms of energy. Okay, so once I show you the velocity profiles, then the cyan one is actually the leader. So that's Johan. Okay, and you can see that Johan met this traffic jam about 25 seconds earlier than the car had, the green vehicle, which is actually me. And then the truck was responding to me in this case. Okay, so Johan went through the jam, made some braking, and went away. We didn't know about it. Okay, we didn't see that. We didn't have the infrastructure support, and we was outside of the range of our communication, so we couldn't use this information. And it would have been nice if we did, because once you see the energy, actually we didn't do well in terms of energy. So this is the energy per unit mass. So it allows us to compare the different vehicles, and you can actually see that the lead vehicle did much better. So if we could predict what is going to happen and we use those predictions and then we respond to them in a smart way by optimizing our controller on the truck, we actually could have saved a lot of energy and actually would have done much better than the green vehicle and maybe even better than the leader. Some scenarios, even that's possible. Okay, so there is a huge potential here now, because by building this infrastructure, we can actually connect these vehicles. They can start to be able to talk to each other. And that allows us to basically exploit this new information through connectivity and actually save a tremendous energy. As a matter of fact, of course, this is not the only benefit we are seeing from such a connected infrastructure, but this is our kind of pitch, and this is how we start to build it up and try to demonstrate. Okay, so just a little timeline here. So we are planning this project, this deployment project, to be 2 years. We started this year in May. Okay, so the first year, or first half a year, sorry, we actually spent by collecting a lot of data. Okay, so with these onboard units, again, as I showed you, we created an RSU deployment plan, so we know what we want to do. We built this traffic prediction algorithm. So once we start to get the data flowing, we're actually able to utilize the data. And as I showed in the last experiment, we also collected some data with the truck. And then very soon we are planning to deploy, we are talking about it, the MDOT. And then we can start to test the communication and develop new message sets, which we would like to, as a matter of fact, standardize with the help of SAE. And then we can actually move ahead next year with the mass deployment of all the RSUs, testing the overall communication loop, and developing the controllers for the truck. And at the end, after a lot of testing and integration, there we are planning to have a final demonstration. Okay, so with that, thank you very much for the attention. And again, thanks for CCAT for supporting us, and for Navistar, Ford, Comsigna, and DOT to helping us to achieve this goal together. I'm very happy to answer any questions.
Hey, Gabor. Looks like we have a question from somebody in the audience who's asking, were all of these tests performed with the PC5 side link, or was 5G NR protocol used?
So, and this point, we were not utilizing the 5G yet. Okay. I hope that I answered the question with that.
Yeah, the next question from the audience was regarding the traffic prediction. Is there a minimum saturation of CVs that would have an effect on the HVs to improve speed, safety, etc.?
This is a very interesting question. Thank you for that. So as a matter of fact, indeed, these vehicles influence each other. Now, when we are talking about these CVs, so that just, or we call them CHVs, connected human-driven vehicles, well, they do influence the flow, but we are not controlling those vehicles, okay? The truck itself, of course, it does, and the penetration of that is important. So we do have some penetration studies regarding how many of these connected automated vehicles needed in order to actually influence the flow. And we also seen that with low penetration of automation, if we have connectivity available from other non-automated vehicles, we can actually see large benefits on the traffic. One more challenging things here is the implementation, right? Because at that point, you're not just collecting data or just focusing on a single vehicle, but you start to look at the overall flow. So but the results are very promising. I didn't show slides on that today. Well, we found that it's actually great that we can use these vehicles, and by actually adding connectivity and this long-range connectivity, we can see benefits for very low penetration of automation, because we expect connectivity to increase fast, but automation is probably going to follow with a slower pace. I hope it answers the question.
Yeah, thank you. We have another question in the audience. They're asking, where are the next steps on your research? I think they want to know where they can find it, if that's available.
I guess I kind of tried to do that in the not the last slide, but the one before. So I think this is kind of maybe the next step on this project, right? So that's what we try to do here. I think the next step of the research is, of course, it's important that these things are scalable, right? So at this point, we are looking at a single corridor, and we want to make our impact there. But hopefully, if these ideas take off, then it can be expanded for larger urban areas where, of course, more science and math has to be brought in. I think we started scaling up from a vehicle to a few vehicles. Now we're going from a few vehicles to a corridor. But eventually, you can think about large urban areas where you can really make large impacts. And of course, as you go from across the scales, the models are changing and the objectives are often changing. So hopefully it answers the question.
We have a question from an anonymous attendee about the traffic prediction model. Is the prediction accuracy a parameter of traffic flow over density? Is it possible that a shock wave experienced by the leading vehicle a few hundred meters ahead doesn't propagate to the go vehicle?
Absolutely. So that's a good question, because here, when I was talking about this predictability, I was actually talking about mainly like whether such predictions is possible. So if you are outside of that prediction horizon, then you have no chance to get predictions. But when you are inside, sure, you can do predictions, but what's the quality of them depends on many things. And indeed, it is possible that some of these waves are actually amplified, and that means that if a leader experiences something, then the follower is going to experience something harsher. But it's also possible that sometimes the leader experiences something and the follower is actually experiencing something less harsh. In technical term is often called string stability and string instability. So what it means is that you need higher fidelity models to actually make these predictions reliable, and those models may be based on first principles or maybe data-based method, or the mixture of the two, because that's what we believe at this point is going to be maybe the best solution to this problem.
Okay. We have a question. What is the time horizon for traffic speed prediction or forecast for this project? Did you use 4G communication as shown in one of the diagrams?
Okay, so there are two questions, right?
Yeah.
So the first one, I tried to answer the first one first and not to forget the second one. So the horizon, as I mentioned, the horizon does depend on basically the how far those other vehicles are. Our goal here is, for practical reasons, that if a truck is reaching one RSU, right? Then imagine the other RSU is maybe about 3 kilometers ahead. Then we would like to provide the truck with about a 3 kilometer preview. Okay, so that means a few minutes, such that it actually has some predictions before it reaches the other RSU, right? So that's kind of the goal here, to achieve this few kilometers ahead. And then the question about 4G, what we use the 4G for, and we do use that, is to communicate with our RSUs. Okay, so the RSUs and the OBUs, they are communicating to each other using CV2X technology. And then we are communicating with the RSU using 4G. Essentially, on the internet, we can connect to this device. So that's what the 4G piece is at this point. That's not to communicate between the RSU and the device.
Okay, great, thank you. What is the range over which you need communications to reduce these shockwave type effects? So this is addressing a question from earlier that you answered.
Yeah, so and it's actually interesting because it's kind of asking this is a different question, but the answer is actually very similar. So because these waves are forming on a few kilometers, right? So that's kind of the scale we are talking about. That means that we kind of need this information through the few kilometers. So again, we are not having the effective, we are not having a physical range of being a few kilometers, but by these infrastructure support, we can actually achieve that. So again, both in terms of predictions, looking ahead a few kilometers, and both in terms of control, looking behind a few kilometers. That's kind of the spatial scale we are thinking about it.
Excellent, thanks. We have a question in the Q&A section. Are your communications using the 1609.2 security certificates?
Of course, this is standardized, right? So there are different standardization levels of the communication, and there are different technologies use certain standard up to a level and then maybe diverge at some point. Okay, but the idea here is that how the information is sent, also what are the message sets. We essentially using standardized technology. So that means that, you know, and it was a very, very important part of this project. So rather than building up our own radio system, which only works on a few vehicles we really wanted to make sure that this is available technology.
Great, thank you. I think that's all the questions that we have. So thank you, Gabor, for presenting this important research to our audience. The research page for this project is now accessible on our website, and the link can be found in the chat box. So while you're there, make sure you follow us on LinkedIn, Twitter, and YouTube to get notified about our upcoming webinars and events, including the 4th annual CCAT Global Symposium, scheduled for April 12th and 13th. Thank you everyone for joining us today, and we hope to see you next time.
Thank you very much.
Thanks, everybody. Thanks, Gabor.